Let's look at some common notation for derivatives. Well, we already saw that we can refer to the derivative with this f prime notation. If you're given a function with the notation y equals a function of x, then to refer to its derivative, you will use y prime notation. You could also use the d dx notation, df dx, or dy dx to refer to the derivative. So these are the common variations that you'll see to refer to the derivative, and we'll have all four of these in our class. One less common notation, at least for us at the moment, is the d notation. So they can say like df. This means the derivative of the function f of x. Later on for other classes you might come across as derivative notation. So again, this is the first derivative. Later on we'll be talking about the second derivative or third derivative or fourth derivative, and we can use the same notation to talk about those higher order derivatives. For example, if we're looking at the second derivative, using the prime notation, if you're taking the second derivative, we'll refer to that with f double prime of x. If you're using y equals a function of x notation, you'll use y double prime to refer to the second derivative. For our d dx notation, it's a little different. So we're taking the derivative of f twice with respect to x twice. Notice that for the numerator, the 2 is wedged in between the two letters, while the 2 on the denominator is at the end. And for our dy dx notation, the second derivative will look like the derivative of y twice with respect to x twice. And in capital D notation, you would tell the reader, take the derivative twice of my function. Now, we are going to explicitly define what it means for a function to be differentiable. F of x is differentiable at x equal to a if f prime of a exists. But what's f prime of a? F prime of a is the limit as h goes to 0 of f of a plus h minus f of a divided by h. So if this limit exists at x equal to a, then your function is differentiable there. We'll be using this definition to highlight when a function is not differentiable. In particular, let's take a look at the graph of y equals to the absolute value of x. In example 6, we have f of x being equal to the absolute value of x, and we're asking to find the derivative of this function. Let's start off by sketching our function. So the absolute value of x looks a bit like this. To help us do the analysis, consider that the absolute value of x is simply sort of two lines. It's made up of two lines. On the right hand side, this is the line y equals x. On the left hand side, this is the line y equals negative x. For our derivative on the right hand side, it's the slope of the tangent line to the function y equals x. But if you have a line the slope of the tangent line is simply going to be the slope of the line. For the line y equals 1x, the slope is 1. So for the right-hand side, the derivative is equal to positive 1. On the left-hand side, using a similar argument, the slope, your derivative, is going to be negative 1. So on the left-hand side, the derivatives are always negative 1. On the right-hand side, the derivatives are always positive 1. Cool. But what about at 0? So for that, we would have to compute the derivative at 0 by using the limit as h goes to 0 of our function evaluated at 0 plus h minus our function evaluated at 0 divided by h. Try plugging in 0 in for these h's. You would get 0 over 0. That's an indeterminate form. It's not really clear who wins. To get some clarity, instead of taking the two-sided limit, let's look at the limit from the left-hand side and then from the right-hand side. So if we're coming in from the left-hand side, our expression simplifies to the absolute value of h divided by h. And if we take values of h a little bit to the left of 0, over here, those values of h are going to be negative. So if h is a negative number, what happens when you take the absolute value of h? Like, let's say you took the absolute value of negative 3. What do you get out? You get positive 3 out. So what you get out is going to be the opposite of whatever you had in. So for this absolute value of h, what you get out is going to be the opposite of what you had in. And h over h gives you 1. So you're taking the limit as h goes to 0 from the negative side of 1, negative 1, and your limit's going to be negative 1. So from the left-hand side, your left-hand limit is negative 1. Similarly, if you came in from the right-hand side, if you took the limit as h went to 0 from the positive side, again, we would have the absolute value of h over h. Oh, and we're considering values of h that are to the right of 0 over here. So these values of h are positive, and when you take the absolute value of a positive number, you get out that same positive number. So this becomes the limit as h goes to 0 from the positive side of h over h, which is simply 1. So the limit is going to be 1. From the left-hand side, the limit is negative 1. From the right-hand side, the limit is positive 1. These guys do not match. Therefore, the two-sided limit does not exist. So again, our derivative at 0, which is that two-sided limit, does not exist. So for this function, the derivative is perfectly fine on the left-hand side, perfectly fine on the right-hand side, but at this point here, at 0, 0, at that sharp corner, the derivative does not exist. And this motivates the argument for why the derivatives don't exist for functions at sharp corners. So whenever you have a sharp corner function, the derivative will not exist there. These sharp corners are often called cusps. So again, the derivative at a cusp does not exist.